Suppose we have a society of 7 people. How many ways can we choose a president, a vice president, and a treasurer trio? So if the 7 people are these 7 polygons, how can we pick the 3 leaders? One way to do this is to enumerate or list out all possible ordered triples like this. But this doesn't seem very efficient. Isn't there a better way? Couldn't we perhaps use some of the elementary counting principles to figure out the total number of triples? In this video, we'll learn about 2 basic combinatorial objects. To begin with, let's investigate k-permutations. A k-permutation of a set S is an ordered list of exactly k elements coming from S, and we don't allow ourselves to use any element twice. We let p and k represent the number of k-permutations of a set with n elements. Let's see an example. Let's find the value of p53. That is, let's find all of the lists of length 3 coming from a set with 5 elements. Again, one way to do this is just to list them all out. But when we list them out this way, we see that the product principle would be a possible avenue to do this. To use the product principle, we realize that we can build a list in 3 stages. The first number in the list has 5 choices, the second has 4, and the third has 3. Since the number of choices is independent from the previous choices at any stage, we multiply them to get a total of 60 such lists. Of course, there's nothing special about 5 and 3. We can repeat the process to find the total number of k-permutations of an n set. In this situation, we have k spots to build our list. The first spot has n choices. The second spot has n-1 choices, the third has n-2 choices, all the way down to the final spot having n-k plus 1 choices. Again, we multiply all these together, and we get this formula for the number of k-permutations of an n set. A couple of things to note. We note that first of all, p of n0 is by convention equal to 1, and Pn, n, which is the product of all the integers from n down to 1, is denoted with an exclamation point and is called n factorial. Using this notation, we get a nice formula for p and k of the form n factorial divided by n minus k factorial. This is a formula for the number of k permutations of an n set. Let's see how to use permutations to help us in answering a counting problem. Let's count the number of ways that we can place 4 rooks on a 4x7 chessboard in such a way that no rook can attack another. Here is one such layout. Notice, all we need to do is to make sure that no row contains 2 rooks and no column contains 2 rooks. Here are a few more configurations of non-attacking rooks on the chessboard. It turns out we can answer this question using an ordered list. Our list is going to consist of 4 spots, 1 for each row in the chessboard. Then, in each row, we have 7 spots in the first row, and 6 spots in the second row, 5 spots in the third row, and 4 spots in the fourth row. We can multiply these together because the number of choices at any stage is independent of previous choices. We see that we get a nice formula of the form 7 factorial divided by 3 factorial for the number of ways to order the chessboard. In particular, p and k always counts the number of ways of placing k non-attacking rooks on a k by n chessboard. While k-permutations count ordered lists, sometimes we want to have unordered selections as well, so let's investigate k-subsets. A k-subset of a set S is an unordered collection of exactly k elements of S, where we don't use any element twice. We use this notation right here to represent the number of k-subsets of a set with n elements. We refer to this as n choose k. Let's find the value of 5 choose 3. This counts the number of subsets of a 5-element set that have exactly 3 elements. One way to do this again is just to list them all out, and we see that there are 10. But once we do this, we realize that for each of these subsets, we can actually order them, and we can order each of them in 6 ways. This is because each of them has 3 elements, and therefore they have p33 or 3 factorial such orderings. As we complete this table, we see that we are generating the 3 permutations of a 5 set using the 3 subsets. Therefore, the number of 3 permutations of a 5 subset fits into a grid that is 3 factorial by 5 choose 3. So we can build the number of permutations by first selecting 3 elements from 5 and then ordering them in 3 factorial ways, giving us the formula 5 choose 3 times 3 factorial. Of course, there's nothing special about 5 and 3. This is a theorem in general. We see that P and K can be obtained by first choosing K elements from N and then ordering those K elements in K factorial ways. Therefore, we get that P n K is equal to N choose K times K factorial. But we can use this to solve for N choose K, so that N choose K is P n K divided by K factorial, or N choose K is equal to N factorial divided by K factorial times N minus K factorial, using our formula for permutations that we learned earlier. This is a formula for the number of K subsets of an N set. Let's see how to count using subsets. Let's count the number of northeast lattice paths from 0, 0 to 2, 3. This is the number of straight line paths starting at 0, 0 on the integer grid and going to 2, 3 on the integer grid, but only moving north or east, that is only right or up. The first thing we can do is that we can just draw them all in this small situation to look for some patterns. One thing you might notice is that each lattice path has exactly 5 steps, and 3 of them are up in blue, and 2 of them are always right in yellow. Therefore, every lattice path can be encoded as a sequence of R's and U's, where R represents a right step and U represents an up step. These are the list for each of the lattice paths. There are 10 such lattice paths. But now we have something to count. We see that northeast lattice paths from 0, 0 to 2, 3 correspond to strings of R's and U's of length 2 plus 3 with 2 R's and 3 U's. But we can find these by just selecting 2 unordered positions from 2 plus 3 spots where we'll place the R's, and the rest have to place the U's. For instance, each subset listed here corresponds to the positions of the R's, and we must put U's elsewhere. Therefore, the number of lattice paths from 0, 0 to 2, 3 corresponds to the number of 2 subsets of a 5 set, and so there are 2 plus 3, choose 2 of them. Of course, there's nothing special about the numbers 2 and 3. We can generalize this to do lattice paths from 0, 0 to the point A, B, as pictured here. Let's count these this time. Once again, we see that as we list them all out, every path is going to have A plus B total steps. And we're always going to take A steps to the right and B steps up. So all we have to do is select A positions in a binary string of length A plus B, where we'll put the right or east steps, and the rest will be up north steps. The theorem we have is that A plus B choose A counts the number of lattice paths from 0, 0 to AB. Let's finish with one more counting example where we can show how to combine the new objects of permutations and subsets to answer a combinatorial question. How many distinct 8-letter strings can we make from the word Colorado? A first attempt that's incorrect is to try to apply the product principle directly. We know that there are 8 letters, so we're just going to have 8 stages to build a string. For the first letter, we have 8 choices, then 7, then 6, then 5, then 4, then 3, then 2, then 1. So we might think that our answer is the number of 8 permutations of an 8 set, which is P88 or 8 factorial. The problem with this is that we've counted the same string multiple times because of the repeated letter O. For instance, if we color the O's, we see that there are actually 6 different ways to get the string Colorado. We get the same string, but because the O's are different color, they get counted different times. We need to somehow deal with the O's first, and the fix is to use the product principle. We'll select where the O's go first, and then we'll order the other letters. This is a 2-step process. First, we choose 3 positions from the 8 to place the O's, and then we order the remaining 5 letters with P55. So we see that the total number of distinct 8-letter strings that we can make from the word Colorado is 8 choose 3 times P55, or 8 choose 3 times 5 factorial.